Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your channel Chandan Physics. In this video, we are going to discuss total internal reflection. Let's begin. What is the phenomenon of total internal reflection and how we get polarized electromagnetic waves from that of unpolarized electromagnetic waves by the method of total internal reflection. First, we have to understand the phenomenon of total internal reflection. Let us consider two such medium medium 1, medium 2, medium 1, refractive index n1, medium 2, refractive index n2. And the refractive index of n2 is greater than n1. Here n2 is greater than n1. Sorry, n1 is the denser medium as comparison to that of n2. So n1 is greater than n2. It is denser medium. This one is rarer medium. Normal to the interface, that is the interface with separating these two media. This one as the interface. When an electromagnetic wave is incident on the interface from a denser medium to that of rarer medium, then at that of situation n1 is greater than n2. That's why we can say n2 divided by n1 will be less than 1. So from Snell's law, here we obtain the phenomenon of refraction. This is angle of incidence theta I, and that be the angle of refraction or angle of transmission theta t. K incident, K transmitted. From Snell's law, how we apply Snell's law? Refractive index of that medium n1, sine of the angle theta I is equal to refractive index of this medium sine of angle of that one. Therefore, sin theta I by sin theta t is equal to n2 divided by n1. As we say, n2 divided by n1 is greater than, sorry, less than 1. Therefore, sin theta I is less than sin theta t. So, theta I is less than theta t. The angle of incident is less than that of angle of transmission. What it clarifies? That equation, when we increase the angle of incidence, gradually there will be the increase of the angle of transmission. At a particular point, at a particular angle of incidence, at a particular angle of incidence, that angle of transmission, this is the angle of transmission, will be 90 degree. At a particular angle of incidence, this is the particular angle of incidence, the angle of transmission will be 90 degree, and that angle is called critical angle, and it is denoted by theta c. Okay. Hence, for a particular value of angle of incidence, angle of incidence theta I, the angle of refraction, the angle of refraction becomes 90 degree, becomes 90 degree, that is theta t is equal to 90 degree, then this value of angle of incidence, this value of angle of incidence is called critical angle. And it is denoted by theta c. So, what is critical angle? This is the angle of incidence in that of denser medium. Though we obtain the angle of refraction as 90 degree, then that angle of incidence is called critical angle. Again, from the relation, again from the relation as the sin theta I divided by sin theta t is equal to n2 by n1, from that of Snell's law, or sin theta I, as we say, that is theta of c, critical angle, sin theta t as 90 degree is equal to n2 by n1, sin 90 1. So, sin of theta c is equal to n2 by N1 from that of Snell's law, that is a relation number 1, again by using the Snell's law under that critical angle condition. So, when we increase the angle of incidence, means that angle of incidence is greater than that of critical angle, then that angle of refraction or angle of transmission, that ray within this medium 1. From the experiment, from the experiments, it is found that if the angle of incidence is greater than equal to that of critical angle, then the electromagnetic wave traveling from denser medium to that of rarer medium, from denser medium to rarer medium is totally reflected back. Into that of same denser medium. When that angle is greater than that of critical angle, that ray is reflected back to that of same medium. That angle is greater than that of critical angle, so that ray reflected back to that of same denser medium, totally reflected back into same denser medium, into same, which one is denser medium. And this phenomenon, what we observe here, is nothing but total internal reflection. This phenomenon is known as total internal reflection. This phenomenon we call total internal reflection, means when the angle of incidence is greater than that of angle of critical angle, then if that electromagnetic wave is traveling from that of dense medium to the rare medium, then it is totally reflected back, and that phenomenon is nothing but our total internal reflection. And this type of phenomenon, an important point here we can notice, this phenomenon is independent of the orientation of electric field vector. In the incident wave. What it say? either the electric field vector either perpendicular to the plane of incidence or parallel to the plane of incidence, but there will be no such change to that total internal reflection. Means total internal reflection is independent of whatever be the orientation of the electric field vector. This is the phenomenon of total internal reflection. Then how we can get polarized electromagnetic wave from that of unpolarized electromagnetic wave by that total internal reflection phenomenon. Okay. Let us see from equation number 1 and equation number 2. From equation 1 and equation number 2, you can notice that sin theta I divided by sin theta t is equal to n2 by n1, which is equal to sin of theta c. Means sin of theta c is equal to sin of theta I divided by sin of theta t, which is nothing but n2 by n1, that is greater than 1. When theta I is greater than theta c, anybody can say it as when theta I is greater than theta c, so that value is greater than 1. What will be the maximum value of sin? Maximum value of sin is 1, but sin of any real angle can never be greater than unity. So that theta t, since that ratio is greater than 1, but we clear there will be not maximum value of sin as 1. So we can say that theta t, that is the angle of refraction, the angle of refraction is imaginary. An important point you can notice here, that angle of refraction is imaginary. Then that line is must take correction. Sin of theta c is equal to that one. So we have to require sin of theta t, sin I theta c. Okay. Then cos theta t, as we say theta t is imaginary, sin not be imaginary, that's why cos theta t is equal to 1 minus sin square theta t under root cos square theta plus sin square theta is equal to 1. Therefore cos theta t is equal to 1 minus sin square theta t under root. Taking minus as common, in place of sin theta t we put its value as sin theta I divided by sin theta c square minus 1 under root minus 1 under root, as I say that is I imaginary number, sin theta I divided by sin theta c square minus 1 under root, that indicating cos theta t is purely imaginary. So, we can show that how we obtain polarized electromagnetic wave. Means technically we can say what be the phase difference in between the parallel as well as perpendicular orientation of electric field vector. Let us proceed. Case number 1, when E vector is perpendicular to the plane of incidence, then from the Fresnel's equation, this is the amplitude of that of reflected electric field vector to that of amplitude of incident electric field vector at that of perpendicular situation. That will be the equation, Fresnel's equation. Under this condition, when electric field vector is perpendicular to that of plane of incidence. Here we consider non-magnetic medium. In non-magnetic medium, the permeability of that of medium 1 is equal to the permeability of that of medium 2, which is nothing but the permeability of free space. Use that condition, we can say the refractive index of medium 1 is equal to relative permeability of medium 1 into relative permittivity of medium 1 under root. So, relative permeability of medium 1, that is permeability of medium 1 divided by permeability of free space into relative permittivity of medium 1, this is the permittivity of medium 1 to that of permittivity of free space under root. Under this condition, mu 1 is equal to mu 2 is equal to mu naught. In place of mu 1, we substitute mu naught cancel out, we obtain epsilon 1 divided by epsilon naught under root. Similarly, for that of n 2, it is under root of epsilon 2 divided by epsilon naught. That is why n 2 by n 1 is equal to under root of epsilon 2 divided by epsilon 1. So, that equation now changes to, in place of mu 1 and mu 2, we substitute mu naught, taking the LCM in that of numerator side and denominator side, mu naught under root cancelled out and we have that form. Next, dividing epsilon 1 under root in numerator and denominator side, we obtain this one and we substitute the under root of epsilon 2 divided by epsilon 1 as n 2 by n 1, n 2 by n 1. As we say previously, cos theta t is purely imaginary, cos theta t is purely imaginary. So, in place of that term, we can write as a minus I b divided by a plus I b, whereas a as cos theta I and b as n 2 by n 1 cos theta t. So, its magnitude term, the magnitude of that complex one as a square plus minus b whole square under root divided by a square plus b square under root. So, the magnitude of that complex number as 1. Therefore, the magnitude of reflected electromagnetic wave amplitude is same as the magnitude of the incident electric field amplitude. The magnitude of the amplitudes are same. Next way, in that of denominator side, there will be the complex one. To avoid that complex one, we have to multiply the conjugate on both numerator and denominator side. So, multiplying a minus I b So, multiplying A minus IB in both numerator and denominator side, A minus IB, A minus A minus IB whole square, A square minus B square plus 2 IB next A square minus B square, as I square is equal to minus 1, in that of numerator side it will be A square plus B square. Now rearranging it, real part and imaginary part. Next, again that complex form A minus IB divided by A plus IB can be written as R into e to the power minus I delta perpendicular. So, e to the power minus I delta perpendicular as cos delta plus cos delta minus I sin delta. When R is multiplied, it is R cos delta minus I R sin delta. Equation number 2. Comparing that equation number 2 to that of equation number 1, when we compare that equation number 2 that of equation number 1, we obtain R cos delta is equal to A square minus B square divided by A square plus B square. Here is the real part, as R cos delta is equal to A square minus B square divided by A square plus B square, and R sin delta in that of imaginary part 2AB divided by A square plus B square. Now squaring and adding. So, R square cos square delta plus R square sin square delta is equal to squaring it and add these two terms. R square as common, cos square delta perpendicular plus sin square delta perpendicular is equal to this, taking the LCM and add these two terms, cos square delta plus sin square delta 1, here A minus B whole square, formula A plus B whole square minus 4AB, A plus B whole square minus 4AB. So, 4A square B square minus 4A square B square cancelled out, and this term cancelled out. So, we obtain R square is equal to 1. So, R is equal to 1. Again dividing these two terms. So, sin delta perpendicular divided by cos delta perpendicular is equal to tan delta perpendicular is equal to 2AB divided by A square minus B square. Therefore, as we first use that one, EOR divided by EOI at perpendicular situation, which is R into that term. So, R is equal to 1. So, we obtain e to the power minus I delta perpendicular, which is equation number 3. Now, from the trigonometric relation tan theta as 2 tan theta by 2 divided by 1 minus tan square theta by 2, here in place of theta we substitute, that is delta perpendicular. So, tan delta perpendicular is equal to 2 tan delta perpendicular divided by 2 divided by 1 minus tan square delta perpendicular divided by 2. Now, tan delta perpendicular by divided by 2 is divided both numerator and denominator side. So, in that of numerator side it will be 2 divided by 1 divided by tan delta perpendicular divided by 2, 1 by tan theta, that is cot theta. So, cot delta perpendicular divided by 2 minus 1 tan cancelled out. So, tan delta perpendicular divided by 2. Next, from that of relation, as we say, tan delta perpendicular is equal to 2AB divided by A square minus B square, A square minus B square. To compare to that equation number 4, we can now simplify it as AB is divided. So, when AB is divided in that of numerator side, so it will be 2, and when AB is divided in that of denominator side, so A square divided by B minus B square divided by B. So, we obtain tan delta perpendicular is equal to 2 divided by A by B minus B by A. Now, we can easily compare equation number 4 and equation number 5. We obtain tan delta perpendicular divided by 2 is equal to B by A. Okay, tan delta perpendicular divided by 2 is equal to B by A. When we obtain that one, by taking the consideration as E vector is perpendicular to the plane of incidence. Next one, when E vector is parallel to the plane of incidence, then what be the phase? Similarly, in case number 2, when E vector is parallel to the plane of incidence, similarly from that of Fresnel's equation, EOR divided by EOI at parallel situation, that much. But non-magnetic medium, we substitute this one, and proceeding in this way we obtain that form, and again we use the complex notation as A minus I beta dash divided by A plus I beta dash, whereas A is equal to cos theta I as usual previously we done, and B dash is equal to N1 by N2 cos theta t. And significantly when we taking the magnitude, then it will be 1, and its magnitude amplitude of both these are equal. Again same way we write in the form of e to the power I delta parallel, whereas r is equal to 1, then we obtain tan delta parallel divided by 2 is equal to beta dash divided by A, as we previously derived tan delta perpendicular divided by 2 is equal to beta by A. Here tan delta parallel divided by 2 is equal to beta dash by A. From the above discussion, what we clarify? From the above discussion, it is found that the amplitudes of reflected wave is equal to the amplitude of incident wave. Here is the relation, the amplitude of this one is same as the amplitude of that one. So, the amplitude of reflected wave, amplitude of the reflected wave is equal to the amplitude of incident wave. In other words, we can say, the wave is totally reflected, the wave is totally reflected at the interface where the angle of incidence, is greater than the critical angle. When the angle of incidence is greater than that of critical angle, then the wave is reflected to that of same medium, as we mathematically show it. The amplitudes of reflected wave is equal to that of amplitude of incident wave. Then we show what be the phase difference in between the perpendicular as well as parallel components of that of reflected wave. Next, the phase difference between parallel and perpendicular components of reflected wave is given as delta be the phase difference, then that is delta parallel minus delta perpendicular, dividing 2 on both sides. So, delta by 2 is equal to delta parallel minus delta perpendicular divided by 2, and taking tangent on both sides. So, tan delta by 2 is equal to tan delta parallel by 2 minus delta perpendicular divided by 2 tan A minus B. What be the formula? So, tan A minus tan B divided by 1 plus tan A into tan B. So, that formula is used, tan A minus tan B divided by 1 plus tan A into tan B. Usual substitutions can be made. So, tan delta parallel by 2, as we obtain tan delta parallel by 2 B dash by A, B dash by A, then tan delta perpendicular by 2, tan delta perpendicular by 2 B by A, B by A divided by 1 plus B by A into B dash by A. Taking the LCM, 1 by a is common, b dash minus b divided by 1 by a square is common, so a square plus b into b dash in that of bracket term. Under simplification we have 1 by a into a square, so 1 a cancel out, so a whole into b dash minus b divided by a square plus b to b dash. Then the values of a, b and b dash are substituted. What are these values? As we say, a is equal to cos theta I, b is equal to n2 by n1 cos theta t, and b dash is equal to n1 by n2 cos theta t. These values are put here. Simply the value of a, b dash and b are put. Next line, cos theta t as common in that of numerator side. And here under simplification n1 cancel out, n2 cancelled out, n1 cancelled out, n2 cancelled out, cos square theta t. As we say, cos theta t as imaginary, then in that of under root term, in place of sin theta I divided by sin theta c, in place of sin theta c we can substitute n2 divided by n1. First we say that sin theta t is equal to sin theta I by theta c. So sin theta c is equal to sin theta I by theta t. Therefore in that of under root term, that will be n1 by n2 sin theta I square minus 1. That one is used here. So cos theta I into n1 by n2 minus n2 by n1 into, in place of cos theta t we substitute this one, n1 by n2 sin theta I whole square minus 1 under root. Now I is used as we know that cos theta t is imaginary, the value only put it, plus cos square theta I plus in place of cos theta t as usual that value, when we square it we obtain that one, n1 by n2 sin theta I whole square minus 1. Simply we write it as cos theta I that under root term as the power half into, in that bracket term we common n2 by n1, so in this bracket we obtain n1 square divided by n2 square minus 1 cos square theta I as 1 minus sin square theta I plus squaring that one, n1 square divided by n2 square into sin square theta I minus 1 plus 1 minus 1 cancelled out, and in these two terms, in that of denominator side, sin square theta I as common, n1 square divided by n2 square minus 1, numerator side as usual terms, and this bracket term we obtain n1 square by n2 square as common. Finally we simplify it, this cancel with that one, so cos theta I n1 square divided by n2 square under root, we have n1 divided by n2, so n1 divided by n2 into n2 divided by n1 cancelled out, so we obtain only that value. What it signifies, that with the required expression to calculate the phase difference between the perpendicular as well as parallel components of electric field vector. So that phase difference between the parallel and perpendicular components of reflected electromagnetic wave reflected electromagnetic wave depends on the angle of incidence. The angle of incidence, whereas theta is greater than that of critical angle. So we can obtain the polarized electromagnetic waves that is either circularly polarized or elliptically polarized. That depend upon what be the phase difference and the amplitude of that reflected wave. From unpolarized EM waves by total internal reflection. Total internal reflection. What is the circularly polarized and elliptically polarized? In later chapters, or we can what is circularly polarized and elliptically polarized, that are discussed in upcoming videos. The chapters named as polarization of electromagnetic waves. So we can say that by the phenomenon of total internal reflection, we obtain polarized electromagnetic waves from that of unpolarized electromagnetic waves. As we say, there will be a phase difference in between the perpendicular as well as parallel components of that of electric field vector. Then we obtained that result. So here with the help of this video lecture, we understand the concept of total internal reflection. First we understand what is the phenomenon of total internal reflection as the idea of critical angle. When the angle of incidence is greater than that critical angle, then we observe the phenomenon of total internal reflection, and then we clear how total internal reflection is useful to us to get polarized electromagnetic waves from that of unpolarized electromagnetic waves. Case number 1, when E vector is perpendicular to the plane of incidence, from Fresnel's equation the amplitudes are same. Then we show that tan of delta perpendicular by 2 is equal to b by a. Case number 2, when E vector is parallel to the plane of incidence, from that of Fresnel's equation the amplitudes are same, and tan of delta parallel divided by 2 is equal to b dash by a. Here we clear that the amplitude of incidence wave and the amplitude of reflected waves are equal. So there will be a phase difference. So what will be the phase difference? The phase difference between these two are calculated, and we have a mathematical result, and finally we clear from that of expression as we obtained polarized electromagnetic waves, that is either plane polarized or elliptically polarized, from that of unpolarized electromagnetic waves by the method of total internal reflection. So with this useful and informative notes, let me wind up the session. Thank you.